Hi, everybody. Yeah, I'm Nick. Thanks for coming to my talk about algorithmic art and Rust. Before we get into the art and we get into the Rust, I'd like to share kind of my journey about how I got here. So I do Rust things for work. These days I work on... Yeah, hey. All right, you want to see the title slide? Oh, title slide. All right. Yeah, so I do Rust things for work. These days I do the intersection of Rust and WebAssembly, and I like to make fast things. I like to make robust and reliable things. I like to create tools that have good developer experiences and support many different use cases and help other people build fast, robust, and reliable things. And I love my job, but it's a lot of serious business, right? So what am I doing in my spare time outside of work? Flashback to a year ago or so, I'm mostly writing side projects in Rust for fun. But these side projects tend to be kind of like semi-related to things I'm doing at work. And then they had this tendency to actually just become part of work. And I had this realization that I was just working the whole time. This isn't a recipe for a well-rounded life, right? So I took up pottery as a hobby. And the physicality of getting my hands dirty and getting the clay in between my fingers really appealed to me. But I wanted something that couldn't turn into work, something that didn't have stakeholders or users reporting bugs or requesting features, something that was just for me where I could relax and have fun. And what I liked about the pottery process was that every step along the way from lump of clay to finished piece has so much depth and so many facets to it that you could spend a lifetime really digging into it. If you love throwing on the wheel, you can make these long skinny vases and play with shape and form, or you can even make your own glaze from scratch like Matt Fiska did with this piece here. And in particular with glaze, what I liked was that it often felt like the whole was greater than the parts. There's this sort of element of surprise because before you fire the piece, the glaze is kind of chalky and it's dull. And then after it comes out of the kiln, it's glassy and shiny and colorful. And you can combine glazes, by mixing them together, or you can layer one glaze on top of another glaze. And at some point, I discovered that if I put a thin layer of black glaze on top of my green glaze, I got something that was kind of metallic and shimmery, almost like an oil slick. And neither glaze alone had this property, but you combine them together and something new emerges. I liked this effect so much that I tried to recreate it with a series of 5 different bowls. But only one actually survived the whole process into a finished piece. And it's because it turns out that pottery is quite difficult and it requires a lot of patience. Things can break at every step of the way, and when they break, it tends to be irreparable because unlike software, you don't have these niceties like undo and version control. This difficulty is really part of the craft, and it's what makes these really beautiful pieces that get finished so impressive because of all the work it took to get there. But I had this personal realization, which is that despite all of these things that I really loved about pottery, I was getting more frustrated by the difficulty than I was relaxing and having fun, which were my original goals. So I'd kind of heard of generative art or algorithmic art, where people would write programs to generate images or little animation loops or maybe music. And I recognized that there was kind of a similarity with pottery and kind of that surprise of combining glazes. Because generative artists are often searching for a set of very simple rules that when you combine them, they kind of create emergent behavior that's bigger than any of those single individual rules by themselves. I think a really good example of this is Process 13 by Casey Rees. And the way that this image is generated is kind of behind the scenes. There's actually a simulation of a bunch of circles moving around. And whenever the circles overlap or kind of touch each other, a line is drawn from the center of one circle to the other circle. No code says, draw these trellises or create this echoing spiderweb effect. This is something that emerges from the process to delight us and to surprise us. And I could look at pieces like this and really appreciate their beauty, both on an artistic and technical level. But I wasn't quite overcome by the urge to make this stuff myself yet, because there's still something missing for me. There's nothing physical that I could hold in my hands. And that's when I discovered pen plotters. So a pen plotter is a robot. It has an arm and a hand, and you take a pen and you put your pen in the robot's hand, and you say, please draw something for me. And then kind of crucially important, it actually draws what you ask it to. And so now you can actually have a physical pen and paper artifact of your generative algorithm. And I think that this physical pen plotter medium actually allows for even more emergence than software does, because there are more variables that you don't have complete control over. For example, a pen doesn't draw perfect Euclidean lines with zero area. Different pens have different widths. They have different colors. A ballpoint pen is going to draw a different line from a fountain pen, is going to draw a different line from a marker, it's going to be different from a gel pen. And ink bleeds, and so you have to kind of grapple with that. Or maybe you can purposely move your pen even slower to get more bleeding and kind of use that as an artistic effect. Colors combine just like the ways you can combine glazes. And maybe you draw a blue line on a yellow line, and now you have a unique green that you don't have any marker to draw. The only way to get that is through combination. I think that this piece by Paul Rickards really takes advantage of the medium superbly. The way that the rectangles overlap and the colors combine kind of suggests a transparency and a depth, kind of like a third dimension, that doesn't really exist in the code. That only comes out once you put it on paper. And this physicality of the pen plotter medium, this is what I was missing from generative art in general. And so at this point, I'm hooked, and I make my decision. I want to make algorithmic art, and I want to bring it into the physical world with a pen plotter. So I bought an AxiDraw, which is a popular pen plotter these days. But at this point, I have a whole lot more excitement than I have knowledge. I don't actually know how to get the pen plotter to draw something. And what I learned was that the easiest way is to use SVG. SVG stands for Scalable Vector Graphics, and it's an image format. But unlike most image formats that you might know, like JPEGs or GIFs, it doesn't talk about pixels at all. SVG talks about shapes and paths, and these shapes and paths are described within an abstract coordinate space. And what the pen plotter can actually do is it can scale that coordinate space up and down to the size of the paper that it's drawing on, or the size of the drawing that you're making, and then it will draw those scaled shapes and paths. So how many people here know HTML or XML? All right, everybody, that's awesome. So as you can see, SVG is also a text format that features many pointy brackets. So basically, everyone who raised your hand, you've taken your first step towards being a generative artist. And this is actually the Rust code that generated that previous SVG snippet, because I don't want to take any old SVG off the internet and plot that. What I want to do is I want to generate my own SVGs, and I want to do that with Rust. So if you search crates.io for SVG, the first hit is the SVG crate, and that's what's used here. It gives you this really nice builder-style API for kind of describing and composing SVG elements. And you can get surprisingly far using just the SVG crate. So what this is doing is it's actually drawing a triangle. And the data is a sequence of strokes in the coordinate space. And this is ultimately what controls the pen. So it says, move to this point, and then draw a line to that point, et cetera. The path element is sort of like the styles for the strokes. So what this is saying is that these strokes should be thick and they should be blue, and then the area that's inside should be filled in pink. And then finally, the document is sort of the whole SVG image and describes what kind of box in that coordinate space is ultimately rendered as the image. Now, to get the SVG from your computer to the AxiDraw, I use this tool called Saxi. And it gives you this really nice web front end for kind of controlling the pen's up and down height and kind of centering on the page. And I can't recommend it highly enough. If you're using an AxiDraw, use Saxi. And so here's the results of rendering it. On the left, that's a software rendering of Triangle SVG. And on the right, this is a photograph of Triangle SVG as drawn by the pen plotter with gel pen on black paper. And so we said that these lines should be thick and they should be blue and that the inside should be filled pink. And yes, the software renderer did that, but the pen plotter can't because it can only draw with the color of the pen that you gave it, and it basically ignores any sort of fill. So now that I can generate SVGs and I can plot SVGs, I kind of set an exercise for myself. How many different ways could I fill a rectangle with interesting pattern of strokes, where I parameterize this fill by like a darkness value, where a 0 darkness value means basically empty, there's no strokes in there, and a 1 darkness value means it's completely full and there's just strokes covering the whole thing. So basically, how many implementations of this trait could I make? Here are a few of the results. So this is rectangle 8 with darkness values 0.1, 0.5, and 0.9. And the algorithm to generate rectangle 8 is to move some distance d along each of those outer edges of the rectangle. And so now you have 4 points, and you connect those points into a new quadrilateral. And then you continue recursively on that new quadrilateral until basically everything meets up in the center. This is rectangle 2, and the algorithm for rectangle 2 is to choose a random point within the rectangle and then start generating boxes outwards until it meets the corners of the outer rectangle. And so if you have like a lower darkness value, you'll get fewer boxes that are kind of spaced a little bit further apart, and you do a higher darkness value, well, there will be more rectangles that are packed really closely together. And now that I had a bunch of ways to create rectangles, I wanted to see how can I combine them together. And you can do that by tiling them. And then I could vary that darkness value in how many different interesting ways could I vary the darkness value for a tiling. This is tiling 0 of rectangle 10. And the darkness value for a particular rectangle within the tiling is determined by which row it appears in. And so the very top row has a darkness value of 0, and the very bottom row has a darkness value of 1. And then it kind of interpolates as you go down the rows between 0 and 1, and you get this vertical gradient effect. This is tiling 3 of rectangle 2, and the darkness for a particular rectangle within this tiling is determined by how close is it to the center of the tiling. And then a little bit of random noise is introduced to kind of perturb the results and make it appear more organic. And what I really like about this one is that it kind of has this kaleidoscope effect that maybe looks like stained glass, or even ripples on some geometric water, right? And I like this because I wasn't intending to get that. It just kind of emerged from the tiling, and I liked that. So this was my favorite of the tiling exercise, and I decided to plot it. So here's a photo of that same image as drawn by the pen plotter with black ballpoint pen on white paper. After plotting, I was kind of hit with another surprise, which is that the lines drawn by the pen were much thicker and darker than the lines drawn by the software renderer. And so it doesn't really look like stained glass so much anymore. It's almost like there's a ghost-type Pokemon that's kind of materializing from another dimension or something, right? But it's cool either way. And so I think when you're starting something new, often the hardest part is like staring at a blank canvas and simultaneously having an infinite number of options of things that you could do, but also not even knowing what those infinite things are. And I think the best thing to do in this situation is to completely sidestep the problem by defining some set of constraints, and then as an exercise, fulfilling those constraints in as many ways as you possibly can. So how many ways can you fill a rectangle? How many ways can you create a custom brush stroke that follows a given path? How many ways can you visualize Perlin noise, which is a noise that gives you smooth gradients of values instead of just random values? How many different kinds of random walkers can you create that move through your coordinate space in interesting ways? Maybe one is a particle with random force applied to it. Maybe another is a pendulum that swings but then randomly chooses to swing from the other side and it moves around. And then once you have these kind of base things, how can you combine them in interesting ways? Can you tile the rectangles and then vary the darkness value in interesting ways? Can you take the path drawn by one of your random walkers and feed that into one of your custom brush strokes? The other thing that I think I really took away from this is that you don't need much to start making plotter art. You don't need to learn a big framework like processing or P5.js or Nanu or open frameworks. You can just start doing this stuff now. And so these first pieces were made with just the SVG crate. And SVG is already a pretty rich language for making drawings. And I mention this because learning new frameworks can be intimidating. They tend to have wide API surfaces and many concepts to learn. And sometimes the best way to start something is to just hit the ground running. And then later, once you have a problem that a framework can solve for you, maybe that's the time to reach for the framework, right? So for example, as we saw with triangle.svg, plotters don't support all of the features that software renderers do for SVG. And so software renderers will fill in shapes with colors or gradients, but a plotter will only draw that outline, and it can only do that in the pen's color that you give it. And if you want kind of a fill, well, you have to do that yourself, and you need to describe that in actual lines that the pen plotter is going to draw, such as like a crosshatch pattern. And software renderers will draw elements in order, so a later element that's drawn on top of an earlier element can actually cover it up and it can occlude it. And with a plotter, it will also draw those elements in order. And the result is that you'll draw the first element and then the second element, and you have two elements drawn on top of each other. And so if you want occlusion with the pen plotter, you have to actually do that in software before you even give it to the plotter. And you need to only generate paths that are not covered up by anything else. And so when you start running into these sorts of problems, like now is the time to reach for a library that helps you out, or to find a framework that will do this stuff for you. Or you can create your own personal framework like I did. I started digging into the rabbit hole of computational geometry and kind of collecting my utilities together. And I named this set of crates Fitzgerald's Art. But as a name, Fitzgerald's Art was really just too bloated. And so to release some of that pressure, it became Fart. So, yeah. Hence the flatulence in the talk's title. But I promise this is the only fart joke in this talk, and nothing else is going to slip out. So I follow a few people on Twitter who do microscope photography art. This photo is actually an extreme close-up of aspirin crystals, like aspirin like you'd take for a headache. And it was taken by Carol Roulard. What I really like about this photo is the way that there's these kind of zones of crystals that fit together, and there's these kind of lines radiating out from their centers that almost look like exploding fireworks, and they have this kind of colorful pinwheel effect going on. I think this is really quite cool and very inspiring, and so I would like to make some plotter art that's inspired by crystal microscopy like this. And these zones really remind me of Voronoi diagrams. A Voronoi diagram is a partition of the two-dimensional plane where you have a set of seed points. And those seed points are the black dots in this image. And then for every infinite point on the plane, you color that point by which seed it's closest to. And the result are these zones similar to our crystal photo. And this makes sense because you can create a Voronoi diagram by doing kind of like a parallel flood fill outwards from each of those seed points at the same time, at the same rate, and until they run into something else from another seed. And this is kind of intuitively similar maybe to the way that a crystal is growing outwards until it hits another crystal and it can't grow anymore. And so we can use this understanding of Voronoi diagrams to actually design an algorithm for generating crystal-inspired art. And so what I came up with is this. Choose n points to be your seeds, and then for many more m random points, for each of those, find which seed is closest to it, and then draw a line to it. And the hope is that these lines are going to create that sort of exploding fireworks aesthetic. And so this simple algorithm actually works pretty well. Here it is plotted on black paper with white gel pen. And already I can see the resemblance, right? I can see the zones, I can see the fireworks. The only difference from the algorithm that was just presented is that these lines aren't going all the way to the seed. They're kind of stopping partway just to give it a little bit more breathing room and be a little less crowded. And next, I wanted to get more crystals of varying sizes, smaller and big ones. And so my idea for that was, like, what if I assigned each of these crystals, or each of the seeds, a gravity level? And well, it didn't really come out at all how I intended, but I think it looks kind of cool. It really doubled down on maybe the explosion style. So ultimately, it's a happy little accident. The other thing to note is that I introduced an attempt to copy the pinwheel effect. And so what this is doing is it's not just drawing a line to the center regardless. It looks at what is the angle from this point to the seed. And then based on that angle, it varies the length of the line to kind of create that two-tone pinwheel effect. This is another variation where now we're only choosing points from within a circle. And maybe it looks like a contaminated petri dish, I don't know. But I think maybe this is my favorite of the series, so it's kind of cool. And this final variation is using colors for that pinwheel effect directly. And so the AxiDraw can only hold a single pen with a single color, right? And so to plot this, I had to actually split out each of those colors into different SVG layers. And then in between plotting each of those layers, I manually switched out the pens to switch the color. And so this is, I think, 3 or 4 layers right here. So there's this kind of famous saying that good artists copy, but great artists steal. And since I'm really new at this, I'm happy to aim for just good. But I think the lesson here is to find inspiration in something and then copy it. And maybe that something is somebody else's plotter art that you want to learn how it works, or maybe it's some vintage 1960s plotter art that you want to bring into the modern era. Or maybe it's translating something that's completely unrelated to computers and to plotters into the plotter medium. For example, maybe the patterns of cracks on the glaze of some pottery piece that you really like. Or maybe it's the way that plants and flowers and leaves kind of grow in this mathematical way. But I would be lying to you if I said that I only had a string of easy successes and it was smooth sailing the whole time. So earlier, I kind of presented the process as write a Rust program, and then you use that Rust program to generate an SVG, and then you plot that SVG with the pen plotter, and everything goes right every time, the first time. And of course, that's grossly simplified. I don't write perfect programs on the first try. Sometimes people say of Rust or Haskell or languages with interesting type systems that if it compiles, then it works. Unfortunately, I haven't found that to be the case because I haven't figured out a way to encode my aesthetic taste into something that the borrow checker can check at compile time, right? But kind of more fundamentally, often what I'm doing is I'm searching for emergence. I'm looking for the unexpected. I'm trying to be surprised. And so I don't actually know what it is that I should be encoding into the type system yet because I haven't found it yet. And so what's really happening is that there's this feedback loop where I generate some SVGs, and then I look at the SVGs and I say, this is cool, oh, that's not cool. I go back and I tweak the program, and then I look at the new SVGs and I go, oh yeah, even more of that. And back and forth, right, until I'm happy, and then I plot it. But the problem is that this feedback loop is really too slow, and it involves a lot of manual work on my part, right? I'm editing the sources, and I say, hey, Cargo, please compile this program, please run this program. And then if there are no errors and it generated an SVG okay, I have to Alt-Tab to Firefox, and then I have to refresh so that I actually see the new SVG, and then I Alt-Tab back to Emacs when I'm ready to make changes. And I don't have timing data for how long one iteration of this loop took, but if I were to estimate, I'd say it'd probably be at least 3 or 4 whole seconds before I was ready to kind of respond to anything and kind of do the next loop. So luckily, this nice person, Benjamin, wrote an article about what kind of tooling and infrastructure you might want when you're doing generative art, and lays out how to solve a bunch of problems, including this kind of instant feedback problem. And his advice is use a file watcher. And whenever you change any source file in your project, automatically recompile the project, automatically rerun it, and generate a new image. And if it compiled okay, and it generated a new SVG image okay, then actually save that image in your repository and make a git commit, just automatically. And so this way, you never lose any image that you'll ever generate, and you have exactly the code that generated that image. So maybe you're riffing on one idea right now, you can always go back at a later time and riff on a completely different idea. And this is exactly the kind of thing that you cannot do with pottery. So I implemented a command line tool for the Fart framework, and I really enjoy saving all of these images and stuff, and it did speed up my feedback loop a little bit, but it really didn't solve the problem. This doesn't look that different from the last version of the feedback loop. And so it's like, yeah, I'm not manually kicking off compiles, and I'm not manually running the program, but I am still waiting on those compiles to finish in this language that's kind of infamous for not having great compile times, right? And I'm still doing all of this context switching with this alt-tabbing back and forth, and I'm still refreshing manually. So I actually wanted to dig into what kinds of commits am I actually making? And so I looked at a random sample of commits from one of my projects that was using the file watcher tool. I went through each of those commits, and I categorized what kind of change was that making. And it fell into just 3 buckets. Algorithmic changes are sort of the beefier changes, things that are changing loops or introducing if-elses and these sorts of things. Constant changes are me saying, oh, I'm using this normal distribution that I'm sampling random numbers from. What if the standard deviation was 0.5 instead of 0.6? How would that affect the image? And formatting changes are me running Rust format, essentially. And I kind of knew deep down, but to have empirical evidence that I'm spending the majority of my time, like 60% of my time, waiting on compiles to change 5 into 7, it kind of blows my mind. So what I really wanted was some way to have constant values in my program that I could actually change in between runs of the program without recompiling the program. So I invented this brand new thing, which I call user constants. You might know them by the name environment variables. But user constants aren't just environment variables. There's kind of some infrastructure that goes along with it to kind of make the whole process really smooth and fast. And so that starts with a local server. And the local server serves up a web UI. And every time the generative program uses a new user constant, it creates a form input dynamically in the web UI, which is kind of what's on the left here. And you can actually go into that form input and tweak the constant value. And this is going to create a post request from the web UI to the local server. The local server is going to update the environment variable. It's going to rerun the program to generate a new SVG. And then the local server is going to send that new SVG back to the web UI where the preview is refreshed automatically. Additionally, I discovered this simple, effective thing that some people call window management. Yeah. So now I'm actually running split screen with Emacs on one side and the web UI on the other side. And so I don't need to do all this context switching anymore because I just kind of have everything at my fingertips now. And so for constant tweaking, which were 60% of my changes, right, the critical path for my feedback loop is now just edit the constant and then essentially look at what the image is that's updated. And technically, yes, I do need to rerun the program, but it happens automatically for me. And I'm not waiting around for the program to finish running, right? This is Rust. Unless we're doing something pretty bad, it should be pretty quick. And so the previous screenshot, it says it took less than 10 milliseconds to generate that image, which is really just barely human perceptible. So finally, my feedback loop is near instantaneous. And as a result, I'm able to explore more ideas faster than I previously could. And that's helping me make new pieces that I'm increasingly happy with, such as this one. And at the end of the day, I have a hobby that is not work, something that's just for me. And I'm having fun making algorithmic art with Rust and bringing it into the physical world with a pen plotter. I hope my story has inspired some of you to try your hand at plotter art or generative art in general, or maybe even pick up pottery. But I think a lot of these takeaways are kind of generally applicable, not just to artistic programming, but professional programming and maybe even other domains as well. Can you define constraints for yourself to make a problem smaller or easier to solve? Can you break something down into pieces? If you want to learn something, try copying it. If you want to bring fresh new ideas into your domain, copy something from another domain. And if you want to boost your efficiency, you should treat your iteration time actually as an optimization problem, and you should profile and gather empirical evidence about what you're doing and what you're waiting on, and then you should customize your tools or even build your own custom tooling to make that faster. Here are a few resources that I found helpful that you can peruse on your own time if you want to get more into generative art and plotter art. And that's everything I have. Thank you very much.